Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello teacher, hello students. Welcome to today's lesson on properties of definite integrals. In our last lesson, we learned about the fundamental theorem of calculus, which states the relationship between the two main operations of calculus, differentiation and integration. Differentiation refers to finding the derivative in mathematics, while integration is a method of determining the solutions of definite or indefinite integrals, such as calculating the area between the curve of a function and the x-axis. We learned that in the first part of the theorem of calculus, which is also known as the first fundamental theorem of calculus, shows us that an indefinite integration can be reversed by a differentiation. We also learned that the second part, which is also known as the second fundamental theorem of calculus, allows us to find the definite integral of a function by using one of its many antiderivatives. Let us watch a video to help us understand this theorem.
All right, well now it's time for me to tell you about the fundamental theorem of calculus. The theorem that really links together the two ideas, the idea of the derivative and the idea of trying to find areas. And basically, to think about this, let's begin with this picture. We want to find the area under the curve and above the floor, above the x-axis between A and B. And here is the answer. So the answer is, if you want to find the area, remember how we write this? I write that the area is the sort of the sum from A all the way up to B of the area under f of x dx. And remember how to think about this. The way you think about this is I'm summing up a lot of small rectangles. They have height f of x, and they have a very, very tiny base change in x. So this is base times height, and I'm summing them up from A to B. So that's the area under the curve. And what does it equal? Well, it turns out that this equals nothing more than capital F of B minus capital F of A. Now I've got to tell you what capital F is. Well, where capital F is the antiderivative of little f. So where capital F is the function whose derivative is f of x. So to find the area under a curve from A to B, the first thing you do is find the antiderivative, and then take that answer, take the antiderivative, plug in B, the right-hand point, and then subtract off what you get when you plug in A. This is the fundamental theorem of calculus. This is the fundamental theorem of calculus. That areas under curves are nothing more than the antiderivative evaluated at one endpoint, evaluated at the other endpoint, and then subtracted.
This leads us right into today's lesson on definite integrals. Both differential calculus and integral calculus are connected to the fundamental theorem of calculus. Within integral calculus, there are two types of integrations: the indefinite integral, which is also called the antiderivative, and the definite integral. The indefinite integral, or the antiderivative, is used to find the function that has an unknown derivative. Hence, the antiderivative title. The definite integral is informally defined as the net signed area of the region in the xy plane bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b. These principles of integration were independently created by both Isaac Newton and Gottfried Leibniz in the late 17th century. Definite integrals have 5 properties. The first is the order of integration. We can interchange the limits on any definite integral. All we need to do is add a minus sign onto the integral when we do. The second is the zero property. If the upper and lower limits are the same, then there is no work for us to do. The integral must be 0. The third property is the constant multiple, where k is any number. As with limits, derivative, and indefinite integrals, we can factor out a constant. The fourth property is the sum and difference property. We can break up definite integrals across a sum or difference. The last property we are going to talk about is the additivity property, where c is any number. This is a more important property than you might think. One of its main uses is to tell us how we can integrate a function over the adjacent intervals a, c. Please note that c does not need to be in between a and b. Students, let us do an activity. In a moment, you will see a chart. Please match the property names with their corresponding definite integral.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Students, you were correct to match additivity to definite integral number 5. Constant multiple to definite integral number 3. Sum and difference to definite integral number 4. 0 to definite integral number 2. And order of integration to definite integral number 1. Students, let us do another activity so you can begin to explore the properties of the definite integral. In a moment, you will see a definite integral. Evaluate it and let f of x equals x squared and g of x equals 1 minus 1 over x.
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Welcome back, students. Were you able to evaluate the definite integral? If you answered this, then you are correct. In today's lesson, we reviewed the fundamental theorem of calculus and discussed how indefinite and definite integral fits into it. We defined a definite integral as the net signed area of the region in the xy plane bounded by the graph of f. The x-axis and the vertical lines x equals a and x equals b. Thus, a definite integral of a function can be represented as the signed area of the region bounded by its graph. In this lesson, we also went over each property of the definite integral. Well done, students! We have covered a lot of material today, and this is all the time we have for today's lesson. Until next time, thank you, teacher. Thank you, students.